Okay, I'm back with another problem-solving session. Again, I have two problems, and last time I had two problems that didn't go very well. These are A5 and A6 from the 2015 Putnam exam. And I'll see how it goes. I mean, if it takes too long, I might only do one problem. If I can do the first problem easily, then I'll move on to the second one. So first, I'll try to do A5. So let's read the question. Let q be an odd positive integer, and let nq denote the number of integers between 0 and q over 4 that are coprime to q. Show that this number is odd if and only if q is of a particular form. Q is of the form p to the k with k a positive integer and p a prime congruent to 5 or 7 modulo 8. Okay, so it's interesting. So obviously we can count the number of a coprime to q very easily using the Turian function. Here, though, we have this constraint that we're only counting the ones less than q over 4. Yeah. So one... No, that's not true. Because q is not... So I was thinking maybe we can just look at the Turian function of q over 4 and glean some information, but q over 4 is actually not going to be an integer here, so it doesn't seem... doesn't seem reasonable thing to do here. Alright. So how can we count these? My first idea is to get some kind of symmetry relation in the group, that certain numbers of coprime integers should be the same. So for instance, I can have a map which maps x to q minus x. And basically if x is coprime to q, then q minus x is also going to be coprime to q, and vice versa. So that gives me a map sort of from the things that are strictly less than, say, q half, q over 2, and the things that are strictly more than q over 2. So that will give me a bijection. But q over 4 is more tricky, because that map doesn't work necessarily. So one direction I'm guessing is So suppose we try to prove one implication first. We assume that q is of this form. Then we can express nq, I think, in a fairly close form, and q is going to be, we're just going to be counting things that are coprime to p, right? So q over 4 is not going to be divisible by p. So we're just going to have to do I'm thinking maybe some expression like this, though I'm not totally convinced. Like, it's some expression like this, but I'm not convinced this exact expression is correct, basically. And if we want to show nq is odd, I think computing the exact value of nq is probably not what we're supposed to do. What we're supposed to do is pair these integers up with each other in a way such that they will pair up exactly if q is not of this form, and if q is of this form, something is going to be left over. So we want to define some kind of map which is going to pair them. It's not obvious what that map would be. Yeah, if you're trying to map, if it, So summing to Q or some multiple of Q is like an easy way to do it. But summing to Q does not pair these things together is the issue. Like that would just be looking at the inversion map, right? Very, very strange question, to be sure. Yeah, I don't think this approach is very fruitful. I still think there has to be some kind of pairing map that does the job here. I just don't see what it is. Like I'm thinking we can sum them, but that doesn't work. Multiplying them. Yeah, I think multiplying them doesn't work either. It also doesn't go anywhere. So we can try to do it directly. So if Q is prime, so we're assuming that K is 1 now, basically, and you're putting no other restriction, then everything that is less than Q, and in particular less than Q or 4, is going to be coprime. So we will just be looking at the number of integers in this range. And the number of integers in this range is going to be less than 1 the floor of Q over 4, I think. So I'm just checking if that's... No, it's just going to be the floor. Unless it's... Well, it's not evenly divisible by 2 here, so it's never going to be an integer. So yeah, it's just going to be the floor. So if Q is prime, then... And Q is just floor Q over 4. And... Well, let's just think about this. Well, when is floor Q over 4 odd? Well, this... let's... 8 a plus r. Well, we are already used it. Let's say 8 t plus r, whatever. So I'm just doing Euclidean division. Then floor Q over 4 equals floor 8t plus 3 r over 4 equals floor 2t plus over 4, right? Which is 2t if r1, 2, or 3, and 2t plus 1 if r equals 5, 7. So basically, if Q is prime, then we can prove this. Like if you know that Q is prime, then it has to be of this form. So the general argument, I assume, looks something like this. But it's a bit tricky to formalize it. So I think this is also going to be true. So it's going to be Q over 4, except we're going to subtract the things. This is originally what I wrote, but we're just going to divide by P. So we're subtracting the multiples of P, basically. And again, suppose well, the problem now is if I assume that P is, P is 5 or 7 modulo 8, I don't really get an expression for Q, basically, so that's a slight problem. But suppose P is anyway, so I just want to characterize this in terms of what P is congruent to. So suppose and in this case, floor Q over 4 is odd. Well, 1 mod 8 divided by 1 mod 8 is still going to be 1 mod 8, so it's odd, so NQ is even. Well, then Q could be anything, right? Well, if it's squared, then it's just going to be 1, but Q is 1 or 3 mod 8, basically. Floor Q over 4 is odd. Yeah, it's always going to be true, right? It's always going to be odd. Floor Q over 4P. Well, we're going to be dividing 1 by 3 mod 8, and 3 is its own inverse, so is odd, so NQ is even. P equals 5 mod 8, then Q is 1 or 5 mod 8. It's important. Now we don't know if floor Q over 4 is odd or even, but we know that we're going to be multiplying Q by something 5 mod 8. And so we know that floor Q over 4 and floor Q over 4P will have different parities. So NQ is odd. And same thing with basically. So this proves the claim when Q is a prime power. So if we know that Q is a prime power, then, well, odd prime power. And we're only working with odd integers here, so we can assume that. So this proves it for when Q is an odd prime power. There's an equivalence. And it basically comes from the fact that if you multiply, so in these cases, it's easy to see that it's even, and in this case, what happens is that when we divide by P, if Q is 1 mod 8, it becomes 5, if it's 5, it becomes 1, and since we worked out the parities here, that means that the parities get switched, and so when we take the difference, we always end up with something odd. So this proves it for prime power. Now we sort of need to generalize it to when Q is composite, and when Q is not a prime power. So we want to show that if Q is divisible by at least 2 distinct primes, then NQ is always going to be even, right? So now, suppose Q divisible by 2 distinct primes, P1 and P2, and we want to show that NQ, we want to show NQ is even. So how could we go about doing this? Now I'm sort of coming back to the pairing idea I had before, but it seems, I admit that it seems tricky to make it work so, because we don't, we sort of don't know enough. And it's possible that we just need to use the explicit formula that I have here. So I'm wondering, is there some kind of inclusion-exclusion formula? Like, can we write in Q equals some kind of alternating sum? So if we start with floor Q over 4, we subtract Q over 4P for all primes dividing Q, and then we add back floor over Q over 4, P1, P2, and we keep doing that, basically, for all combinations. So I'm trying to figure out what happens if you do that, but it seems kind of difficult to get a handle on the parity of that thing. But actually, no. So, no. Yeah, it's not easy to get a handle on the parity there. I got confused because I thought we could just infer something from the parity of the binomial coefficients, but actually we can't do that, so that doesn't really work. So there has to be an easier argument here. So let's define I don't really want it to be, so I'm trying to put some kind of multiplicative structure on this parity, because it seems like we can get something like, we can set, so yeah, so let FQ be 0 if floor Q over 4 is even, and 1 if floor Q over 4 is odd. Right, so basically FQ equals floor Q over 4 modulo 2. Okay, and then what we can show is I think we can show that f is a logarithmic. So FAB for AB odd is equal to FA plus FB. And this basically comes from this explicit characterization, because or FQ equals 0 if Q13 mod 8 and 1 if Q57 mod 8. And I think this F has this property, which because we can define it as 1, so you can imagine the multiplicative group modulo 8 as a Klein 4 group, and you can define this function as 1 on 5 and 7, and then extend it to the rest of the congruous classes. So I think we get a function with this property. And now we can express NQ as a sum. It's not quite over the divisors. It's more like, it's FQ minus F Q over P plus P over minus, so it's something like this. And now it looks like this is going to be a bunch of copies of So we can write FQ over P as FQ minus FP, right? So then this just ends up being like a decoupled huge sum. Basically, all the sums over all the primes are going to decouple with each other. And we just need to count the number of times that each prime is going to appear in the sum. So FQ because we only care about this modulo 2. So actually the signs don't matter. It's just sum modulo 2. We can get rid of the alternating signs. So how many times does FQ appear in the sum? If we assume that, so suppose we write this as FQ plus FP, and then write this as FQ plus FP1 plus FP2, and so on. P1 not equal to P2, of course. So FQ is going to appear, so once here, and then it's going to appear the number of prime divisors of Q, and then the number of pairs of prime divisors. So Q is going to appear once for every subset of the prime divisors of Q. And if Q has more than yes, so we're also counting the empty subset. That's right. So FQ appears in the sum right. I think this is true. Yeah, this is true. So then, how many times does FP appear? So now let's count this. So here it appears once, right? And FP is going to appear once for every subset that it is in. Every subset of the prime divisors that is in FP is going to appear once, because we're going to be taking the sum once for every subset. So that's going to be, it appears 2 to the d minus 1 times. Okay, so if d is greater than or equal to 2, all FP appear an even number of times. So NQ is 1, 2. Okay, so that finishes the proof, because we've shown everything. We have handled every case. We have proved that if Q is of this form, then it has the property. And we've shown that so if Q is a prime power, then we have shown the equivalence. We've shown the claim that is desired. And we've shown that if Q is not a prime power, then it has at least 2 distinct prime divisors. And then we've shown that NQ is always even. Okay, so we're done with A5. So this is the proof of A5. Now I'm moving on to A6. So this should be interesting. So let n be a positive integer. Suppose that A, B, and M are n by n matrices with real entries, such that AM equals MB, and such that A and B have the same characteristic polynomial, prove that these two determinants are equal with for every n by n matrix X. So my first thought when I see any problem like this is to use some kind of density argument. We know that the characteristic polynomials are the same, and often you can prove identities about determinants by proving them on a dense subset of the matrices and then extending by density argument. But I think here it might actually not be necessary. So let's write down what we know. We know that the determinant of A minus Ti is equal to the determinant of B minus Ti. Right? Very simple. So suppose this polynomial is Pt. Okay. So we would like to sort of plug in T equals X in this formula, but we can't really do that because when we do that, we are actually. So what we want to show is that we can plug in T equals X, right? That's sort of the dream. It seems like we also know, since the determinant is multiplicative, we can multiply by m sort of in any direction. Hold on, this is kind of tricky. Importantly, we don't really know that anything in this expression is invertible, right? But invertibility, sort of lack of invertibility, we can argue away by a density argument, because invertible matrices are dense, and this is a polynomial identity, so we only really need to show it for a dense subset. So that shouldn't be a big problem. A and B having the same characteristic polynomial, I think, does not give us that much information. So yeah, it would be really, really nice if you could just plug in like T equals M here. But the problem is we can't do that. I'm trying to work out if there's a way to use Cayley-Hamilton to like plug in some kind of matrix into this, because we know that we can plug in like A or B, but that doesn't seem to be sufficient to give us what we want. So for starters, we want to show A equals M equals that B equals M. So we want to show a plug-in T equals M here. But even this is actually not trivial to show. It's not trivial. So if M is invertible, then we can probably give some kind of argument like this. So determinant of M times determinant M inverse A minus identity. But actually, it still doesn't go anywhere. We end up having to prove that M inverse A minus I and M inverse B minus I have the same determinant. And we should be able to get that. I mean, intuitively, you should be able to get that from the characteristic polynomial, but it doesn't seem straightforward to get it. So there might be some kind of general fact here that you can always evaluate. So Cayley-Hamilton tells you that you can evaluate a characteristic polynomial at the matrix and it gives you 0. So that's sort of a theorem. But I'm actually not at all sure that this is likely true in general. It's possible that when you have some kind of commutativity relations that it's going to hold. So that's why this kind of theorem might actually hold. But I would like to prove it using Cayley-Hamilton. And it seems to be difficult to do that. Like, I would only want to evaluate this polynomial at like A or B, because those are the places that I know that the polynomial is going to have a definite value, like a value that I can get my hands on. And elsewhere I can't really know what the value is going to be. Let me just work this out. So if you just move M to the other side of this equation, we're going to get this, and we're going to get determinant. Yeah, so we're going to get B minus M. Okay. Let's do this in general then. Suppose that we're dealing with A minus mx, so we can do determinant M, determinant M inverse A minus x, and then we just applied it from the other side. We're going to end up with determinant minus M minus xm equals determinant B minus xm. So the claim holds if M is invertible. But the problem here is M is a specific, so if you fix A and B, like we're not proving a general polynomial identity. We're proving a polynomial identity restricted to a closed subspace of all matrices. So that kind of makes it difficult to use the density argument, because a dense subset might not be dense in a closed subspace. So we can't really use the density argument very cleanly. That means we can't just assume that M is invertible, I think. So if A and B have the same characteristic polynomial, it's actually possible that M has to be invertible. Like, it's possible we can somehow construct some kind of inverse for M, but I'm not sure about that at all. So the problem is we can assume, like what we can cleanly assume is that X is invertible, but it seems that for the argument to work cleanly, we need to assume that M is invertible, and that's kind of annoying. So PA is 0. So notice that in this part of the claim, we didn't need to use the fact that A and B have the same characteristic polynomial at all. We just needed to use the fact that M conjugates A to B. Now, obviously, if we know that M is invertible, then we know for sure that A and B are conjugate. So that, that we know that they have the same characteristic polynomial. So if we knew that M is invertible, this bit of information would actually not be necessary. We would already know that that's true. So since we don't know that, we're given this different piece of information, and we're supposed to sort of make it be enough, if that makes any sense. And one thing we can sort of observe is, so PAM is going to be equal to MPB. I mean, both of these are obviously going to be 0. But PA and PB are both 3, so that doesn't matter. But for any polynomial f, so this is sort of true for, this is B. This should be B. For any polynomial f. So this is true for any polynomial. Yeah, and it seems like we can't really assume that M is invertible in general, because suppose that we can choose A, B, and M to all be 0, and then every condition here is satisfied. And the claim does hold, but M is not invertible, so we can't really assume that M is invertible. That is, we can't prove it from these assumptions that M is invertible, so we need kind of a different argument. So another way to phrase this argument is, suppose we do, well, I'm thinking of multiplying by the determinant of M on one side and on the other side, but that could just give us 0, so that's kind of useless. So suppose we take some matrix like this. You have no clue if this is going to work or not. When you look at this, and this would be determinant AM minus MXM minus KA plus KMX, right? It would be this. And if you do it with B minus XM, and now I'm going to multiply it from this side, basically. I mean, it doesn't change anything, but... And now I'm going to end up with MB minus MXM. This part is going to be the same. And then I'm going to end up with KB plus KXM. Okay. And so we know from the condition that we're given that these two are the same, AM and MB. So this matrix is the same for both of them. And then we have this additional thing here. So the reason I'm adding in this parameter k is so that I can argue that if these are equal as functions, then I can argue that they must be, I mean, m can only have finitely many eigenvalues, so then they must be equal. These determinants must be equal to, like, for all x. But I don't see how to reason that these must be equal. Like, I have to somehow smuggle in the assumption that A and B have the same characteristic polynomial, but I don't see how to do that. Yeah, this is very tricky. Yeah, I also think this idea of shifting by k is actually not going to work. And basically, we need some kind of non-invertible analog of one matrix conjugating something to another, but it seems difficult to get a handle on that. Yeah, I'm just stuck at linking the characteristic polynomial to the problem. I just can't think of an idea to link it. So if these two conditions are true, like we have to be able to say something about M, I feel like, but I'm just not seeing what it is. Yeah, I'm totally out of ideas, I think. Like, this problem has to be very simple. Again, like all of these problems, but I just can't figure it out. Like, there's some kind of obstruction in the way, and I just can't figure out this problem. Because, like, A and B having the same characteristic polynomial is such a weak condition. It seems like I I shouldn't really need much, because M is, like, if M was just invertible, I would just finish the proof, but the proof depends so crucially on the fact that M is invertible that I can't really recover it from that. Like, I guess all I need to prove is that I guess M is invertible matrices are dense among the sets that link, that sort of conjugate two matrices of the same characteristic polynomial together. But I'm not even sure how I would do that. It seems like a very tricky thing to do. And matrices of the same characteristic polynomial don't even have to be conjugate. So you have to assume that they satisfy this relation for some m, and then you have to prove that you can basically choose m to be invertible by an arbitrarily small perturbation. And I don't know how to do that. Like, I don't even know how such a perturbation would preserve this relation, basically. I have no idea. I'm wondering if I should work out some examples, but I doubt it will help very much here. So if A and B have the same characteristic polynomial, I'm just thinking, can I figure out any other matrix that satisfies the same polynomial, right? That is zero when evaluated at the same polynomial. And it's not easy because A and B don't, they don't commute. So if they commuted, it would be easier, I think, to figure it out. But here it's not. And the reason I want that is because I want to use Cayley-Hamilton to deduce something with it doesn't seem to go anywhere. So what do I do? What do I need to carry through this argument? Like, this argument doesn't seem to work directly, which is the problem. It's so frustrating that I can't think of anything, and that I'll think the solution was like totally obvious when I look at it, or when I find it. I just can't think of anything right now. So it's suppose we set m equals to 0. Now, if m is 0, the reason we know that these two things are equal is only because we know that the characteristic polynomial is equal. Otherwise, we would not know it. So that ingredient again is crucial. But the question is, we sort of know how to do it if m is like 0 rank, and we know it if m is full rank, and we're sort of unable to do it if m is in between. Then I'm sort of not sure what we're supposed to do. But I mean, in the end, it has to come down to the fact that the characteristic polynomials are equal. It just has to be more than the fact that the determinant is equal, because that's much too weak to tell you anything. So suppose X is the identity, right? And we allow M to be anything. So M could be any matrix, right? Well, M could be any matrix with this property. So M is actually kind of restricted, which means I'm not too comfortable doing that, but yeah. So technically, I just want some way to set t equals m here, right? But I'm not sure how we do it. Like, this commutation thing has to be a requirement for it, right? But I'm not sure how we justify setting t equals m. Seems kind of tricky to me. So, okay, hold on. So I'll work on this a bit more. Suppose that we write this as, so now I'm going to assume that A and B are invertible, and I'm going to justify why I'm doing that later. But for now, let's work with this assumption. I can do, I want to think about where I want to factor. Okay, so I want to factor it like this. Determinant of A, right? And then I can yeah, I can multiply with A. Actually, anyway, I mean, I end up with this, right? Here. And this is the same thing as this. I could also do it like this. So I could do it A inverse M determinant A, and this would be inverse M determinant B, and then I could just multiply. So I would get B minus A inverse MB, right? And this would be determinant B minus A inverse AM. So this would be the determinant of B minus M. Okay, so here we have a proof if A is invertible. So now I'm going to do something slightly unorthodox, which is that I'm going to take A minus Ti instead of A. And basically this is always going to be invertible. Now I'm leaving this as a matrix over the polynomial ring in one variable. So I'm including T sort of as an indeterminate. And in that case, this matrix is always invertible, because I can always evaluate it somewhere if it's invertible as a matrix over R, so, you know, it's trivially going to be invertible. And because it's just about, you know, this matrix is invertible if the determinant is non-zero as a polynomial, and since it's non-zero somewhere, it's also going to be a non-zero polynomial. So if I work with this, then I get the same result, right? But if you sort of track it, and I can do the same argument because I know that these two determinants are equal, so I'll actually get A minus Ti minus M equals determinant B minus Ti minus M. So that's kind of interesting, because it means that these are equal, you know, these are the same polynomial. So A minus M, B minus M, they have the same characteristic polynomial. Which is a step forward, but it still doesn't really give me the result I want. So it means that I need to push my methods further. Like, if I want to get this result, this is not good enough. So let's now do the same thing. Hold on, I'd want to keep this actually. Let's start with A minus mx. And I'll try to basically do the same thing here. So I'll get A inverse m x determinant A equals determinant A inverse mx determinant B. I'll get determinant B minus hold on, let me clarify this. So evaluate it. So basically this is just proving a very special case of the claim that we want to prove, which is, you know, not super impressive. But now if I'm trying to do this, I'm going to get like A inverse m xb, and, you know, A inverse mxb is just not good enough. Like, right, this is not the result I want to prove. So this trick works to prove that these are equal polynomials, which is nice, but it doesn't, you know, quite give me what I want here. I guess I should just factor out x too, right? So suppose I factor out x. So I'll get x inverse here. And I'll pick up a determinant x. And now I'll write this as determinant x inverse minus a inverse m, determinant b determinant x. And then I want to again get everything in the correct order. So I'll first multiply by x. So that will put x in this position, a inverse m, determinant b, and then I'll get b minus x a inverse mb. And since mb is just am, this is going to be just determinant b minus xm. So it again seems like we got the result we want, but we assumed that x and a are both invertible. It's a crucial detail. And we can't really assume this in general. However, we can do the same trick. So again, this works for any matrix A and B. So we can in particular take A minus Ti instead of A and B minus Ti instead of B, and we'll get the result A minus Ti minus Mx equals determinant B minus Ti minus Xm, assuming X is invertible. And so set t equals 0, we find that determinant a mx equals determinant b xm if x is invertible, and proof is finished by a density argument. Because if we prove this, this is just a polynomial identity in X. So if it's true on a dense subset, then it's true everywhere. Okay, so I'm finally done with this problem. This is, I don't know, I still feel like my proof here is kind of counterintuitive, and I don't really feel like I understand it. So I'll actually check the official solution for this later. But I mean, this solution works. It's just a bit messy. So thanks for watching. I'll see you later.